Now, we talked about prior knowledge that students have that is actually inaccurate. But students have a lot of prior knowledge that is actually accurate. So let's think about how we can use that knowledge as the foundation, as the building blocks for further learning. So it might not be ready as is. We might need to be adapted and co-opted. So for instance, in a mathematics class or statistics, students might be familiar with some concept, but not recognize them immediately because the notation that they've seen in different classes where they first learned them is different. So that's an easy case of just making sure everybody's on the same page in terms of the language. Or sometimes students might have a little bit of prior knowledge, but it's not enough for the whole problem. But it can certainly be capitalized. So for instance, when I start talking about hypothesis testing, I know that hopefully I can rely on knowledge that students have about measures of standard and measures of variability, that they have a sense of means and standard deviations. And they could use that knowledge maybe to start thinking about differences in distributions, differences between two groups, and how big those differences are relative to the variability of the distribution. They might not be able to arrive to the whole concept of hypothesis testing on their own, but that's a knowledge that exists there that can be certainly incorporated. Unfortunately, there's a step that needs to happen first. And we'll see that with this example. This is actually one of the most replicated experiments in psychology. So each card has two sides with letters and numbers on both sides, and we only get to see one side. But we know that if we see a vowel, we know that if we see a letter on one side, then there should be a number on the other side, and vice versa. And there is a rule in this situation. The rule is that if a card has a vowel on one side, it should have an even number on the other side. Now, we're concerned that some cards might be breaking this rule. And so we want to check. We want to turn them over to see if they're following the rule. We also want to be efficient, and we don't want to turn over cards that we don't need to. So the question is, what is the minimum number of cards that we must turn over to verify whether the rule is being followed or not? And so there's 4 options there: A and 6, A and 7, A, 6, M, and 7. So take a second to think about this. So the answer is A and 7. A is a problem because if it has an even number on the other side, it's in violation. 7 is in violation if it has a vowel on the other side. Now, some people get confused and think that 6 might be a problem, but if 6 has a vowel on the other side, it's fine. And if 6 has a consonant on the other side, there's no rule about consonants, so 6 is fine. For the same reason that there's no rule about consonants, M is also fine, and we don't need to check that. This is a hard problem. When I do this in groups with professors, people with terminal degrees, they struggle to come to consensus on this, and it takes them actually significant time. But I am a big believer in redemption and second chances, so I usually give them a second problem to work on to see how they do on that one. So let's look at the second problem. We still have cards with things on both sides, except in this case, these cards in this green problem are stand-ins for students, for people. And on one side, we have their age, and on the other side, we have the drink that they're drinking. And there is a rule in this situation. The rule is if that they're drinking alcohol, they must be over 21. Again, we're concerned that some students are violating the rule. And so we want to ID them. And we also want to be efficient. So what is the minimum number of students that we must ID to verify that the rule is being followed? and which ones. Now, this is a much easier problem. Most people can easily, immediately see that we are concerned about the minor, 16, and the person who's drinking alcohol to check whether they are at least 21. And so people do much better on this problem than on the other problem. But if you think about it, these two problems are very similar. They're not identical, but they are isomorphic. There is a mapping between letters and numbers, vowels and consonants, and odd and even numbers, and age and drinks, and age above and below 21, and alcoholic and non-alcoholic drinks. And the rule also matches. So, because they're isomorphic, what that means is that the mental operations required to solve the problems are the same. So how can it be that one is much easier than the other, takes less time, and most people agree on the solution? People have different explanations for that, but one of the interesting explanations is that we are very familiar with the rule of the drinking rules in the US, at least. We use them all the time. They affect us. Maybe they affect our kids. Maybe they affect our students if we're chaperoning an event. Maybe we've tended bar at some point and we had to pay attention to these facts. The other problem is abstract and does not rely on that rule. But here's the interesting fact. When we go into a school and as students to solve the problems, predictably they don't do as well on the blue problem, the abstract logic problem, than they do on the green problem. But when we give them the green problem first and the blue problem second, but in between we tell them, now that you're solving this problem, think about the problem you just solved. See if there's anything there that helps you with this one. Then the percentage of students who can solve the more difficult problem goes way up. And it's statistically significant, actually. The reason for that is that the knowledge needs to be activated in order to be useful. And that is the same for you, if you think about it. You all had the knowledge of drinking rules if you are viewing this from the US. And it did not dawn on you that you can use that little tidbit in your brain out of the millions of things that are in your brain to help solve that abstract logic problem. So the moral of the story is that most of our knowledge sits there doing nothing most of the time, and that we need to activate it before it can become useful. The good news is that the activation is one of the easy things to do. Just reminding students, like in that example, think of the problem you just solved. Think about the thing you learned in calculus. See how that can apply to this physics problem or this engineering situation. That's all that is needed for the activation, if the knowledge is indeed in the students' minds.